Welcome to calculus. You will master complex problems, but forget how to add. On this episode, Stevenson will demonstrate
We've been studying this idea of what area under a curve represents. And so we have some rate function, and then the area under the rate function over a time interval gives you a total output. So this picture hopefully kind of stays with you. Well, we're going to improve upon that. So what we've been studying here is how we can estimate elements like distance or total area or accumulations, whatever the scenario is, using finite sums. And the way we do that is we multiply using rectangles the functions evaluated that represented the height of each rectangle, and then we would multiply that by the intervals along the x-axis, which was the base of each rectangle. And what we would do then is we would take all of those and we would add them up. What happens if we apply limits? What if we start to increase the number of rectangles? What do you think would happen? Well, we're about to see it. So let's do some notation first. We need to understand that we're going to be adding up a large amount of quantities. So we're going to use some notation called sigma. So sigma is that E looking shape. It's the Greek letter, the capital sigma, and it looks like the E. It means to add up. So the way this would be read is this is the sum of a sub k from k equaling 1 to n. So each of those little a sub n's are just all the different areas under some function. And the k is just telling you that the k is over by sigma. That's just telling you, well, how many you're going to do. They're telling you start at 1, and then n is going to tell you where to stop at. So this could be a picture to help illustrate this summation here. So notice it's all abstract. There's no definitive values. You have a beginning, you have an end, and you have all these little subscripts. So adding up the areas of n rectangles under the curve can be written with sigma, right? That Greek letter. So what does that look like? Well, let's get back to basics. How do we find the area of each one? We're going to multiply to find the area of each rectangle. We're going to multiply the height of each rectangle, which is the function evaluated at each input. Well, in this particular case, each input's just called c sub k. Remember, k is how many you wanted to do. Remember from the previous slide. And we're going to take that height and we're going to multiply it by every base. Well, every base is just delta x sub k. Remember, delta means change. So it's just the change in every sub-interval. And we're going to multiply those together, and that's the area of each of those rectangles. But remember, we're going to add up a lot of rectangles. So we're going to do the sum of that. It's important to note that these areas could be positive, could be negative, or could be 0. It just depends on the function evaluated at each input. So now we need to add all these up. The sum, that's the S sub n, of all the areas can be written using sigma. Remember to add up. And we want to add up a lot of these things. So this says the sum of f of c sub k times delta x sub k from k equaling 1 to n. So that's the area of all of the rectangles under the curve. And this idea of doing these partitions and having all of these rectangles is where the Riemann sum comes from. Now, what do you think happens when you increase the amount of rectangles? So look at the first picture on the left. So we have here just some f of x function, and notice it's below and above. So on the right, you can see it's being partitioned into so many rectangles. Well, what happens if we increase the number of rectangles? What if we increase it again? We're getting lots of rectangles, right? And it can get smaller and smaller. Well, hopefully you're recognizing that eventually all those little rectangles are going to give us more and more approximate answers, and they're getting to the point where they're going to fit perfectly almost underneath the curve itself. Well, if we take the limit of that sum of rectangles, then what we have is called the definite integral. The definite integral is the limit of that sum as n approaches infinity. So we say, let's let those number of rectangles approach infinity. Then we get what's called the definite integral, and that represents your area under your curve. And what's nice about this is if you have a continuous function, then the definite integral will exist. So if your function is continuous on your closed interval, then there's a definite integral also on that closed interval. Now this notation though is not very user-friendly. There is a better way to use it. And if we switch from Greek letters to Roman letters, we get that. So on the left, you have kind of the Greek usage of this definite integral, and on the right, you have some nicer notation using Roman letters. So let's compare. On the left, you have the limit as n approaches infinity of the sum of sigma, right? K equals 1 to n. Now sigma, if you think about it, starts with the letter S. So on the right, you have an elongated S. Now that A and B is the interval you're looking at, okay? Where are you finding the area from? Next, you have the heights of every rectangle. So on the left-hand side, it needs to be C sub k, because remember there were all those different rectangles. But on the right, you don't need the subscripts because you're no longer using sigma notation. So it just becomes f of x. Now you need the base of every rectangle. So we had delta x on the left because remember that was the change in the partitions along the x-axis. Well, we know delta x can just turn into dx, changing the notation there. So this is your definite integral, the area under a curve. So when you see that symbol and it says from a to b of f of x dx, it's asking you what is the area under this curve, which is f of x, from the interval from a to b. Now how do we read this thing? Well, it does have parts. So you can see we have the integral symbol itself, which again is like an elongated s. You have what's called the bounds of integration. The number at the bottom, a, is your lower limit, and the upper limit is b. The f of x, the function itself, is called the integrand. So you're going to hear me use that word quite a bit. Dx, the x in that dx there, is the variable of integration. It is important that the variable in your integration matches the variable in your function. They have to be the same. So in this example, I have f of x, so then you have dx. If your function says f of t, then your variable of integration needs to be dt. Okay, they need to match. This is the integral of f from a to b, and when you evaluate the integral, that means you get out an output or an area under your curve.